Welcome to the CS1033 Program Fundamentals, the final part on use of data structures for problem solving. We will have an introduction to abstract data structures during this part of the lecture series. Let me first go to the contents. I will have an introduction to the abstract data structure concepts with you. Then I will look at three of the most widely used abstract data structures that we come across: stack, queue, and the tree. And in the tree data structure, I'll specifically look at a particular variant, which is called the binary tree. Starting on the stack data structure. So first of all, I would like to remind you that when we talk about abstract data types or abstract data structures, we consider a data structure in terms of how we use it conceptually. So a stack is a familiar thing for us, where we have a stack of things. So it is from that point of view we consider the stack data type or the stack data structure. So essentially, when we are talking about a stack, we will consider the functions we can perform with it. The particular implementation of a stack is not what we are concerned with when we discuss it as an abstract data type. So in a stack, we have the functionality of pushing an item onto the stack. So this item that we are storing in the stack ends up on the top of the stack. So that is the common accepted behavior of a stack. So when we do this, when we store an item on the stack, we should get an indication whether that action we have done has been a success or failure. The reason is practically data structures have a finite size. It is not practical to think that we can have a data structure of infinite storage capacity. So if you take a stack, as they would be of a finite size, there is the possibility that when you try to put a new item on the stack, there is no space left. So that would be an error or an exception which should be notified to us. And if there is no error notified, we can take it the operation has been a success. Then we have the other corresponding opposite operation of removing an item or deleting an item from the stack. So the term we use is pop an item from the stack, and this would essentially give us the topmost item on the stack, because when you look at a stack, what we can see is on the topmost item is a stack of things. So if you consider a stack of books, what you see is the book at the top of the stack. So, and if you put a new book on top of the stack, well, we will start seeing that one. And if we remove something, it is what we can remove, what we can see on the top of the stack. So here again, we would have a error scenario, because if it is an empty stack, when we try to remove an item, we will not be successful. So we should have some mechanism of indicating that failure. Okay, that we try to do an operation which cannot be completed successfully. So for these situations, it would be interesting and it would be useful actually to have other functions such as empty that allow us to check, is the stack empty? Okay, so if we have such a function, before calling the pop function, we can check whether the stack is empty, and if the stack is not empty only, we will call the pop function. Similarly, of course, we can think of a full function which we would be able to call up and see whether the stack has reached its upper limit and whether there is no more space to put an item. And only if there is, if the stack is not full, we will push an item. So keep this exception handling situations in your mind. And a very important functionality we would want to have of the stack is the current size of the stack. So it could be obtained by a length function. So what is the, so it could be the size, it could be the height, it could be the length. So normally you would have some meaningful name given to that function. In addition to these functions, we have another function called the top or the peak. So this is similar to pop with the exception that we would only read what is at the top of the stack without removing it. Now pop would remove the item and give it to you, but top is a function that is not going to remove the item at the top, but will just allow us to look at it. It gives a reference because it is anyway visible to us. Okay. And if you yeah, so it is very important to always remember that the top is a function that signifies this behavior of the stack, that it is just the topmost item that is visible to someone who is using that abstract data type or the abstract data structure. So I have a diagram here which shows the operation of a stack very succinctly. So it's very important to remember these terms like LIFO or LIFO, which very in a shorthand manner indicate the particular operational behavior of the data structure. Now, it could be named as first in last out also, or FILO, but the more common term that we use to characterize a stack is last in first out or LIFO. So let's look at how we can have a stack data structure implemented. So now you must remember we have moved from the basic types and composite types into abstract data types. So basic types are provided by the programming language, for example, Python. It would be the same for any other language, C, C++, C Sharp, Java, or any of these languages. That would be the same. Every language provides us with the primitive data types of integer, real, Boolean, character, like that. And then we are also provided with the composite data types such as arrays, strings, lists. So if you consider the data type such as arrays and strings, they are quite close to the basic data type. So if I'm like listing them, I have the basic data types of the common ones: character, integer, real numbers, Boolean, like that, and of course memory addresses. Then we have the strings and arrays, which are composite data structures, but quite efficiently implemented by a programming language because we use them all the time. Okay, just like basic data type. Then we have the other structured composite types like list, tuple, set. So they could be provided by the language system like Python through a library of data types. that is part of the language system. So you can directly use that actually in your programs. But when it comes to third type, the abstract data types, we have to create them. Okay, so either we have to create them in our own programs, or we might actually have them available to us as library code that we can import. Okay, so so to our program we can import these libraries. Anyhow, someone has to implement this. It is not a core part of the programming language. So let's look at how an implementation can be done. We can use a list data structure, which is a built-in data structure in Python, to implement a stack. So if you are creating a stack, we would require instantiating a stack and initially having it as an empty stack. So here's the straightforward way of doing that. We create an empty list. Okay, so that would give us the empty stack. Then we have a requirement to enter items to this stack. So for that purpose, we can directly use the append method in the list that will perform the push function. So as shown here in this example code, I will keep on appending items to the stack, and it will get stacked in the data structure. Now, the corresponding pop function we can have from the pop function that is available for the list. So this pop function is available for the list. Mind you, there is no push function, so we will have to wrap the append method inside the push function that we define. Okay, so we can define push, and we can pass the particular item we want to put into the push function, and then we will have a colon to indicate that we are now going ahead with the definition of the push function. And inside the push function, as its code, its body, we will simply call the append with that particular item. Okay, so so that's how you can implement the push function, whereas the pop function is directly available to us. Okay, so if I may remind you here, the push will have to be defined by you. Okay, so that would require getting that particular item and appending it, appending that item to our variables, the stack variable, which is actually a list. Of course, here you have to deal with the possible error scenarios, and I'm just not giving the full code here, just to remind you that we don't have a direct push method available. What we have is append. Whereas pop, we have it available directly as part of the list data structure. And length function is available here. So in my sample code, you can see I use the iterate the for loop to iterate through the stack, which is an iterable data structure, because it's a list. So this stack is actually a list. It is iterable. So using the for loop and the range method, I will be iterating through that to access its content. So I can just keep on popping in this manner. So again, remember, if we use a list to implement stack, if we pop from an empty stack, it will cause a runtime error, because if we try to pop an item from an empty list, it generates a runtime error. So the same problem will be there for our this particular stack also. Okay, so you may want to define your own pop function or pop method with the list pop function, but incorporating error handling. Right, so that sample code I have shown here. So here an empty stack is created by creating an empty list, and then I am appending values to the stack. Basically, this is push operations. Then once that is done, you have the list like this. And then whenever I pop, I'll pop values from the tail of the list. So the last one in will be the first one out. So you can see when I iterate through the loop structure, I get these elements. And finally, after popping everything, I will have an empty stack. It is shown here as empty list. But if I try to pop one more time, it will give me an error. It's an index error saying you are trying to pop from an empty list. Right. So that is basically the abstract data type called stack. Okay, we can very easily define it using two key methods, push and pop. And there are additional methods like length is full, is empty, peak. Yeah, but the defining two functions are the push and pop. Okay, and similar to the stack, we have the queue. Here the operation is different because in a queue you enter from the tail and exit from the head. So yeah, that's how a queue is supposed to operate. In Sri Lanka, queues sometimes tend to be a bit differently operated, but in our queue data structure, that is the construct we have. Okay, so similar to the stack, the principal functionality would be insert an item at the tail end of the queue. So again, as I explained for the stack, because we are using fixed size data structures, fixed amounts of memory, we will have to define the size. So therefore, it is quite possible when we try to insert a new item, the queue is already full. We can't do it. So we should return an error condition or exception. Okay. So that has to be notified. And the other one would be removing an item from the head or the front of the queue. So this could also lead to an error if we try to remove an item from an empty queue, because in an empty queue, there's nothing to remove. So that should raise an exception. And of course, we would want to know whether queue is empty. Okay, so that would return a Boolean value. And we would want to find the length of the queue. So this is similar to what we have discussed for the stack. So this is basically the current size. Okay. So there could be another method called size or max size, which tell us this is the maximum size of a queue. Okay, but that all depends on the particular implementation. In Python, when we implement, we don't do that because our lists are dynamic. They grow and shrink as we insert and remove items. So for a stack or a queue implemented using Python language, we will not have a method called size or a max size, because that would not make sense, because we are using a list to implement. And again, we can have, similar to the peak, we can have the value at the front referenced using this front method call. So here the value, the whatever the element at the front of the queue will not be removed, it will stay, but we will know what is there. Okay, so that's the that's the method by which it works. And because unlike a queue, we can also look at the rear of the queue, we can have that function, just like front, which is visible to us, rear is also visible to us. So this is quite different to the stack, where only the top is visible to us. We can't look at what's at the bottom. So yeah, so that difference should be remembered. Okay. Yeah, so as I just mentioned, so this is the abstract idea that in a queue both the front, the head and tail are visible to an outsider. Here's a diagrammatic view. So the short notation which we use for a queue data structure is FIFO, FIFO, which says first in, first out. Okay, so yeah, we could also say last in, last out also. Okay, but that's not a very commonly, LILO is not a commonly used term to describe a queue. And yeah, so essentially this is a sequentially accessible data structure similar to a stack. So stack is also sequentially accessible in that always the element at the top, and here again element at the head of the queue is what we access. In both abstract data structures, we can't access any element out of sequence. So let's look at the implementation of a queue using Python. Again, we can use a list data structure, which is a built-in data structure available with Python, very fast in operation. So to create an empty list, we can simply create a list and initialize it. So the two square brackets with nothing in that is an empty list, which gives us an empty queue. And we can use the append function again for the insert, and that way items are added to the tail of the queue. Okay, straightforward append. Mind you, again, just like in stack, we are not doing any kind of error handling here. So especially because in Python, a list is a dynamically managed data structure. And we can use the pop function, but of course, here we will have to pass the argument 0 to say pop, not from the tail, because if you don't give an argument, Python will pop from the tail. Okay, but by giving an argument 0, we can pop from the head or the front of the list. So that is what happens here, the pop function. So this is essentially remove. So if we want, actually we can have a renamed function. So we will define a function remove, just like so we can have insert also. Here we define a remove function that will return to us the content in the queue at the head. So we have to say what we want is at the element at the 0th location. So 0th index, that is the 0th address, is the first item. Okay, so just to give an idea how that would work. So so we can look at the code for that, right? So this this should again work similar to the stack, but we have to be mindful of the fact that again an error is possible if you try to pop from an empty list. So similarly empty queue, that would give an error. So when creating our programming codes, we have to be mindful of this kind of situations. So I think this is a good time to explain to you the difference in computer engineering with regard to other engineering. So when we build a product, say mostly it could be a software product, but there could be some hardware, like especially in embedded systems. But any system that a computer engineer build, large part of the system would be software. So sometimes it could be 100% software, sometimes it could be like 80% software, 20% hardware, or some other such situation. So when the percentage of software in the system reduces, say to about say 20% software, 80% hardware, it would be more like an electronic engineering product rather than a computer engineering product. So computer engineering product tend to have more software in that compared to the hardware. And electronics engineering would have more hardware and less software. So nowadays it is impossible to find any kind of computer engineering product which does not have a hardware component. And similarly, it is quite impossible to find a electronic engineering product which does not have some software component in that. So given that software is present in all of these product ranges, one very interesting issue in this software is if you consider the software code, quite a large fraction of the code is for handling of exceptions and errors. Okay, so it could be up to 80% of the code is not to do the primary job of whatever the functionality, but to make sure that all kind of errors, exceptions are handled properly. Okay, so this would be quite different from other engineering fields like civil engineering or mechanical engineering. Of course, they do have certain amounts of error handling required in their systems, but the amount of engineering work that goes into such error handling is far less than what you have in computer engineering. So always when we write software, when we do programming, we have to be mindful about these exceptions or error scenarios. So that is an important aspect to remember. So if you look at both our sample implementation of stack and queue with the Python built-in data type list, we didn't do a good job of error handling. Okay, so we have to do a better job, so for that purpose, before inserting, we have to check whether space is available, so that we can do by checking the length of the stack before the availability of space before inserting, and we have to make sure that we don't remove from an empty stack or a queue. Again, that we can check by keeping track of the length. Okay, so now the issue is, if we try to do it that way, we are moving a little bit away from our abstract idea. So when we consider a stack as an abstract data type, we are only concerned about push and pop primarily. Okay, and when we consider a queue as abstract data type, primarily we are only concerned about insert and remove. Okay, so insert at the tail, remove at the head. Stack always insert at the top, remove, push at the top, pop at the top. Okay, so as soon as we start dealing with errors, we have to be aware of all the sizes of the data structure, what is the current size. So that would take away the abstract nature of the data structure, because now we are becoming aware of the internal data structure, how it operates, and now we start making decisions based on that. So yeah, so our preference is actually to maintain that abstract notion. Okay. So to do that, we have to create objects. Okay. So to maintain the abstract nature of these data types, as well as to do a better job of error handling, we will not write the error handling code directly in our main program body, but we will implement Python objects. Okay, so let me quickly give you a rundown on that part along with the code. So here the definition of a Python object we give by defining it as a class. Okay. So I want to give you a quick description of this terminology. When we are writing code, okay, at the time we are writing code, we call an object as a class. Okay. At the time of running the code, that is when you are executing the program, we call the same thing as an object. Okay, so class is what we call instantiated into an object at runtime. Okay, so keep that in mind. So we start off by defining our class as Q, and we first of all define its internal structure. Okay, so the internal structure has 3 items. So let me show you what the 3 items are. Okay, so one is a buffer. Okay, that we create. Okay, so this is where we store our items, and in Python, when you are creating objects, you are provided with a reference to itself. So this self is that. Okay, so we always get this by default. Okay, we get a reference to ourself called self. Okay, so like when you are speaking English, I am a student of University of Moratuwa. I am in the semester 1. I am studying Python. I am are all self references. Okay, so similar to that, we get a self reference to the object called self, obviously. Okay, and in addition, we can pass any other parameters. Here I am passing one parameter called size. So whenever I am initializing an object, that means at runtime, when I'm creating an object using this class, which is a template, I have to pass a value as a parameter, the size. Okay, so I'm storing that size in a variable inside the object, and I'm also defining another variable called length and initializing that to a value 0. And of course, the buffer, as I mentioned, this is a list, and you can see I'm using the multiplier, the repetition operator. Okay, repetition operator. So which we have discussed earlier. So essentially, I am creating a buffer of this size. Okay, so this is a buffer of a single element, and the type is none. So this is a basic element type. So this is basically a reference to a memory location actually, and number of such elements of the size is the length of my buffer. Okay, so it's essentially a list of length size. Okay, so moving on, I will now define a method, a function for the queue to enter an item. So it is called insert. So I have to pass a item to be inserted to this particular when I perform the particular operation, insert operation. So first of all, I will check whether the current length, okay, current length of the object storage is less than the allocated size. Okay, because if the size is equal, if the length is equal to the size, that means there is no more space available for a new item to be inserted. So if it is less, I will proceed and store the particular item that was passed to me as a parameter here at the current index value, which is the same as the length, because this length is essentially giving the next available free location. Okay, so we start with 0. So initially you have at the address location 0 space to put the item, and then we point to the next available location. So self dot length, that variable is incremented by 1 to show, okay, next available location is 1 after this. And now because we have successfully stored the item into the buffer here, we will return a true value saying the insert operation was successful. If that was not the case, if there is no space in the buffer to put this item, we will return false. So we will be returning a Boolean value as the result. Now to remove that was to insert. Now to remove, I will define a method. So first of all, I have declared a variable called item and initialized it as none. Okay, so yeah, so that's a default way of saying this particular variable does not contain anything. And after setting that up, I will check whether the queue is not empty, because if the length is 0, that means we haven't put anything to the queue yet. It's empty. In which case we will return the item, and what we will return is a none. Okay, so we are not returning anything, we are returning none. So whoever calls the method remove can check what was returned, and if it is none, it knows, okay, that was a empty queue. Okay, right. So if there are items in the queue, what we do is we will store the first item. Okay, first item in the queue, that is, the buffer is a list. So the item at the 0th location, I will store that into this variable called item. So this is a temporary variable actually. So after storing it there, I will shift all the items one place forward. Okay, so whatever the item now, so I will loop from 0 to whatever the length minus 1, and what I will do is now I will put into the 0th location what was earlier at the location 1, and location 2 will get whatever at location sorry, at the item at location 1 is the item that was previously at location 2, like that. So everything gets shifted. Okay, this is shift operation. And then because now I have shifted everything by 1 position forward, there's going to be a free position at the end of the buffer, end of the list. So I will reduce the length by 1. Okay, right. So now after finishing this, now the item is now modified with the item that was at the head. So that is what is getting returned. Okay. So now we have a actual item we return, and if we did not go to this particular conditional block, we would have returned only a null. So we have now looked at the insert method, remove method, and we can have other methods like get length, which will simply return the current length. Okay. Here's a test program. Okay, here's a test program to test my queue. Right. So now, because we have defined a Python object, we have to say, no, I have a separate part of the code as my main program. So, so this is how you define that. If name is main, so this is the main object. So first of all, I will create a queue. Okay. You can see I am calling the queue object. This is the Python object called queue with a capital Q. Okay, capital Q. And I am passing the parameter 3, which is the size. Remember, in the definition, there was the self, comma, size. Of course, self is automatically passed by the Python language system. You don't explicitly pass that, it is implicitly passed. So you have to pass only what is after that. Okay. And my variable name is simple q. And then I can call methods on that. So I'm inserting various things. So this from the game Call of Duty, various players are here. So I before starting the game, I am inserting players to the game. Okay, so once the players are there, so if I could not insert any of these players, then of course I can't play the game. Okay, yeah, you can insert any value here. Okay, I'm just inserting strings. So once I'm done, I can check how many players are available. Okay, and then I can use the remove method also. Okay, I can call up remove methods, and this will correctly handle the remove without causing any kind of runtime errors. Okay, so I would like to remind you to write this code. You can of course copy and paste it from the sample text sample code given here in the slide set, and test this out and see what happens when you try to enter. So this is 3 items. Okay, these 3 items. So what happens when you try to enter more than 3 items? This will be the 4th item. And what happens if you try to remove from the queue a non-existing item? Because there's only 3 items in the queue. This is the 4th one being removed. Okay, so test this out and see what happens. As an exercise, okay, you should implement the stack as a Python object. Okay, so I have shown you the code for implementing the queue as a Python object. Do the same for stack. Okay, you can directly use the sample code. Okay, so it won't take much time. Let's move on to the last part of our lecture series on data structure for problem solving. I want to discuss the tree abstract data type with you. The basic data structures that we looked at, like list, tuple, set, dictionary, as well as the abstract data types that we have discussed so far, stack and queue, they are all what we call linear data structures. So actually you can draw it like linear, with a linear representation. A list, tuple, sets, dictionaries, stack, they are all linear in their representation. In contrast, we in our problem solving work, we sometimes want other type of data structures. Okay, so here the linearity is that either explicitly or implicitly you have an element in the front and at the behind. So you might say, no, if you take a stack, as a data structure, it is iterable but unordered. Okay, set is iterable but unordered. So in a way, you might say, oh yeah, what is in front of this element in the set? It is not ordered, no? But because it is iterable, you will get something in front, and because it's iterable, you will get something in behind. So while there is no explicit ordering, there is an implicit ordering, because when you iterate, you will get one after the other. So similarly, yeah, dictionaries, of course, it is governed by the key value. So it is not meaningful to say this is in front, this is in back, because it's all in the it is according to the key value. But it is also implicitly having an element in front and an element behind. So that I have noted here for the sets and dictionaries. But if you take other things like list, tuples, and stacks and queues, so especially list and tuples have indexes. Okay, so they are ordered. Okay, and stacks and queues, by very nature of their definition, they are ordered. Okay, because stack is first in, last out. Queue is first in, first out. So they have linear order. Data structure such as a tree is quite different, okay, from this linear arrangement. So we want to look at this type of different operation. So this data structure we call the tree is a hierarchical data structure, which means it has an order that gives a hierarchy. So there is a top level, there is a level below that, there's a level below that, like that. So it is multiple levels actually. So that is ordered, but according to levels. So you can visualize this as an upside down actual tree. Okay. So yeah. So the so normally tree has branches going like this. With the root at the bottom. So root is where you connect it to the ground. But if you turn it upside down, this is then you get the tree data structure. So here the elements of the tree where we have the data, they are called nodes. Okay, they are called nodes. Topmost node is called the root. And so I explained to you why the upside down business is there. And so if you have a particular node, so here's a node, and then you can have other nodes below that, and you can have a hierarchy of nodes going like that. Let me. So so that so if you are starting off our tree structure, this would be the root, and then all these circular ones are the nodes as indicated here. So just like any tree branching out, no, it need not go all the way down. Okay. And the topmost one here, so this is our root, and all of these are called nodes. For a given node, for a given node like this, the nodes immediately below that are its children. Okay, so these are its children, and of course you can say this is a grandchild. Okay, and the node immediately above a particular node is its parent, and of course then you have the grandparents also. And when we have nodes without any children for themselves, that we call as leaf. So this is a leaf because it has no further children. Okay, so these are the leaves. Okay, so hopefully it is clear to you. It is not necessary that leaves are all at the bottom of the tree. No, it is defined as when you have no more children. Right. So so what kind of applications we have for this kind of tree data structure? Well, quite a lot actually. So many of the data we deal with the hierarchical in nature. Let's take a student record because that, it would be easier for you to understand. So you will stay here in the university for 8 semesters. So if we take your academic record, it is like this particular so this would be the overall academic record, and then you will have a record for each semester 1, 2, 3, like that for all the other semesters. Okay, so 8 semesters, and within each semester you will take multiple modules. Okay, so these are then the modules of your academic record, and then some modules may have additional things. For example, here it could be that you are supposed to take the module, but maybe you got you are not well, and so we are representing some information here, and this is where you took the module finally. So like that. So it depends on how you want to structure, but generally that would be the nature of the data, the hierarchically structured data. In fact, no, every assessment of a module will have 2 major parts, actually 3 major parts. One part is the continuous assessment, which we assess for the final grade. Other part is the continuous assessment, which we don't assess for the final grade, but is part of your what we call formative learning. So as you study over the semester, you learn stuff, and we have labs to check on that. But that is to help you figure out whether you are learning things, and for us to figure out whether we are doing our job right. So that is called formative assessment. Then we have what is called summative assessment at the end of the semester, where we will check whether you have mastered the content. So we'll have written exam, as well as we'll have some labs done at specific points in the semester, which will tell, okay, after week 1 and 2, the student has attained this level of knowledge, like that. Okay, so you can see it's a very hierarchically structured management scheme we have for your academic career here in the university, and the data should ideally be stored like that. Okay, so for many of the areas, whether it is health records, whether it is business records, in any type of record keeping, we have this natural hierarchical structure. So the tree data structure is quite useful to represent that type of data. So another one you encounter every day is when you use your computer or your smartphone, it has a file system. Okay, so file system, so you are familiar with, you have multiple directories. Inside the directories, you have files and other directories, and inside that you have some more directories. So we have a direct structure of subdirectories, and some, in a particular directory, some are leaf nodes, which means files, and some are other nodes, which means subdirectories, which go further. So that is also another very common usage of tree data structure for data representation. For our discussion in semester 1, we will focus on a particular variant of binary trees, particular variant of tree abstract data type called binary trees. Okay, so the difference here is it will have at most 2 children. Okay, so if you take a node in a binary tree, it may not have any children, in which case a leaf node, or it may have just a single child, or it may have 2 children, left and right, not more than that. Okay, so when you have the 2, yeah, they are normally named left child and right child. So this is how we would implement a tree. We will create a node that has 3 parts. Okay, so the node stores some data. Okay, and then it will have a pointer to its left child and a pointer to its right child. Okay, so let me just briefly show this graphically. So this is our node where we will put some data, and this is our left child and this is our right child. Okay, so this is how we would have it. And the node here, we will maintain some data. Okay, and this would be our left pointer to the left child. Okay, so that is the pointer to the left child, and this is the pointer to the right child. Now, if I don't have a left child, this pointer would be none. There is no value given to that variable which store the left child, and similarly the right child. So in that case, this would become a leaf node. Okay, leaf node. That means no more children. So moving forward, the whole tree we represent by single node, which is the root node, because once we give the root node, we will be able to say this is the root node. Then we will be able to find out all the other nodes starting from there. Okay, so we can keep on going down the tree and find. So giving the starting point is good enough. Okay. Yeah, so again, as discussed earlier, to create a binary tree, we can use a Python object. So we have to write the object. So I have a sample code here to discuss with you. The implementation of a binary tree as a Python object. So first of all, I will define my node. Okay, the node object, because a tree, a binary tree or a tree is a collection of nodes, which are arranged in a particular manner. So so here I am defining the class called node, and here's the particular definition for the instantiation. So as mentioned earlier, we will have our self-referencing pointer, and I am passing a key value here. Okay, so this is to identify a particular node uniquely. Okay, so this is just my sample implementation. Okay, Then I have the left child and the right child. So two variables basically, which I initially set to none. Okay, these two variables are set to none. They are not pointing anywhere. And the value in the node I have put as the value I passed as key. So you can pass any kind of data structure here to be stored as the value. Okay, you can pass a tuple, you can pass a list, you can pass anything actually. Okay, but generally what we would pass is a tuple of a key value and some other value. Okay, right. So let's look at the implementation. So I can create the root of a tree by passing the first key value. Okay. So here I have a variable called root, where I create an object instance by passing a string to the node object. Okay, and then I create some more nodes. Okay, so I create a new node called with the value herb, and another one called Homer. So this way I have now basically three nodes created. Okay, first one. This is the second node, and this is the third one. Okay, so three nodes created. I could have created them as node 1, node 2, node 3, like that, and then assign them to variables. But rather than doing that, what I did was, okay, I have one variable called root created, and when I created this node, I assign that node to that particular variable, and that particular variable has a left child and a right child. So when I created two new nodes, I assigned one to left and one to right. Okay, so that's what I did for the purpose of creating nodes. Okay, so every node I have created, this 1, 2, 3 I have noted, have a reference to that particular object. Okay. So I can go on creating a list like this. Okay, so from root, let me just give a brief idea about what I have here. So I had the root, and then from the root I had a left and a right, and then from the right hand side I'm having another left and right. Okay, so this is how I have created my tree. Okay, this is the tree structure. Okay, I didn't create anything on the root dot left or right. Okay, so so once you have a tree like that, you can do interesting things by traversing or visiting these nodes in a tree. Okay, so when you visit the nodes in a tree, you can do it in two ways. Okay, either you can traverse depth wise. Okay, so what is meant by depth wise? So you keep on going down, and when you hit the bottom from one part, then you come back up and then keep going down. So here, yeah, so here if you start here and go to the left, so you go down. Okay, you can't go any further, then that's enough. Oh, that's ends the visit there, and then you come here, and then you go down this way and you come here, and no further visiting is possible. You go this way, and then you can traverse like that. So there are different ways of traversing. Other ways to travel breadth first. First of all, you would visit all the nodes at a particular level. Okay, so you start from here, then you visit these ones, and later you visit these. Okay, so that would be your order in that case. Okay, the breadth first. Um, so to do the depth first traversal, we will start from the root and go to the deepest level. Okay, um, as I explained. Okay, so in the breadth first, we'll just go one level down, cover everything at that level, and then go to the next level like that. So when you do the depth first traversal, okay, where you go to the deepest and then come back and then go to the deepest and then come back and then go to the deepest like that, there are three ways of traversal, which are called pre-order, in-order, or post-order. Okay, so reason why I'm mentioning these traversal methods is this is a key aspect of using a tree data structure, a binary tree data structure, and later I will be giving you examples of how this kind of traversal is useful for solving problems. Okay, of course I give only one example each, but yeah, you can think of other examples. And very interestingly, if you remember in the first lecture series we discussed recursion, we can do this tree traversal in a very intuitive manner using recursion. Okay, so let's look at the traversals now. Let me clear the drawing. Okay, so when you do pre-order traversal, as noted here, you can do that to create an exact copy of the tree. Okay, so when you want to do the pre-order traversal, you can define a function. So here I have defined a function called print pre-order, and when I call the function, I will call it with the root of the tree. Okay, that variable which points the root of the tree. Okay, then what happens is, so this is recursive now. Okay, so I am given a tree. So whenever I am given a true root, it is a tree I am given. Okay, so so if I am at the root, I will print the root. So I can make a copy of the root. Okay, and then I will do the traversal on the left subtree. So let me again draw that sample tree, which will be helpful for me to explain. Okay. Okay, so this is my tree. Let me get the right. So what I do is now I will start with this node. So I call print pre-order with this root node. So so what I'll do is I'll straight away print this particular node. Okay. After that, I will call the method again, print pre-order method again, with this left-hand child as the root. Okay, so I'm again giving a tree. Of course, here it's only a single element, and then it will keep on doing that. Okay, there, and once it finishes going to the left, it will return, and then, for example, here I will go to the so so I will check if root, that means so basically I'm checking whether there is a valid pointer. Okay, if there's a valid pointer, what I do is I will print the data at that particular node, and then I will call the left hand side subtree. Okay, so I will pass a pointer to this node. Okay, so then I come back again here with this particular node. Okay, so I will check whether it is null, or it is none. No, there is a valid pointer here. So I will print this. So this value I will print, and then I will call the left. Okay, mind you, when I call left here, it will be a none. Okay, but I will call with that, and so I will come here with a none value, and I will check it here. It says if none, of course, nothing will be done. I will simply return. Okay, there is no execution happening, and then I will be actually at this point. Okay, and I will call preorder with the right hand side, and again there is no right hand side. It is also null, or the value is none. So I'll come back again here, and it will check it. Sorry, it will check here. So it is none, so nothing will be done. It will return. Okay, so now I have come all the way here. So then I will be returning from the function. So now from here there is nothing more to do, so I will return all the way up here. Now that way I have now finished this part when I was given this particular tree. So now I will give the right hand side subtree. Okay, so I will come to this place, print that, and then go to the left. Of course, now left has a valid value. I'll print that. I will call the left hand side again, that is none. I will return. Then I'll call right hand side, that is none. I will return, and so on and so forth. So you can see I will be printing the nodes in the exact order they appear. Okay, so that is called pre-order. So I can create an exact copy of the tree by doing pre-order traversal. The other method is to traverse using post order. Okay, so this way I can carefully delete the tree. Okay, now for example, if you are trying to delete the tree, so let's say you come here, you delete this node. Now you are in big trouble, because now you have no pointers to this one or to this one. Okay, so you can't use pre-order for deleting. Okay, so if you have delete here rather than printing or copying, you are in big trouble. So in post order, what we do is, first of all, I will keep traversing. So I will come here with the root. Then if that is a valid node, I will go to the left. Okay, and I will keep on going to the left. Once I have gone to the left, to the bottom. So at this point, I will again call this one with left node. That means this particular pointer to the left, it is none. So I return back here. Then I call with the right one. So that is also none. So I return back here. So then after trying to travel this way and trying to travel this way, there is nothing more. I will be coming here. Now I can delete this one. Okay. Once I delete this one, I will be returning here. Of course, I don't delete here. I'm just printing. So I can say delete this node. And then I repeatedly do that. So here again, I go to the very bottom. And after deleting this, only I will come back here. And then after deleting this, I will come back here. So there is, in this deleting, I will not delete any intermediary ones, because if I delete an intermediary one, the ones below becomes what we call orphans, because they don't have their parent and you can't get to them. So post order traversal is done in that manner. So this is the reverse order, which you can see from the earlier one. Not exact reverse, okay, because that was the pre-order, and here we traverse so that we can carefully delete elements one by one. Okay, so So once we do the traversal, say we delete, ultimately we will be deleting the root, and that would terminate the that would remove the tree. And another one is to do the in-order traversal. So you can actually see the pattern here. If you are doing pre-order traversal, do whatever you want to do. This could be printing, this could be doing some computation, this could be copying the node, whatever you do before you call yourself recursively. Okay. And if you are doing post-order traversal, first call yourself recursively to the left and right, and then do whatever you want to do. Okay. So this could be again printing or deleting or doing some computation like that. And in order traversal, first go to the left, then do whatever you want to do. Here I'm just printing, and then go to the right. Okay. So this is what is called the in order traversal. So these are the three different traversal methods available for the depth first traversal. So we discussed two main methods of traversal: depth first and breadth first. And the depth first has three types of traversal, which is pre-order, post-order, and in-order. Okay, so to finish off this part of the lecture series, I have created another exercise for you. So you are given two binary trees. Two binary trees. Basically, you are given root 1 and root 2. Okay, your job is to check if the two binary trees are identical or not. Okay. Yeah, so the way to do that is to actually traverse. So, okay, good question to ask is, what do you mean by they are identical? So for them to be identical, they should have the same node structure. They should have the same node structure, and they should have the same values in the nodes also. Okay. So that is the exercise. So I have some helpful hints here for you. So you can do this by traversing the trees and comparing the values at the current node, current root of the tree, because always you are getting a subtree to work with. Okay. So if the two values are not equal at any given time, there's no need to check rest of the tree. Okay. If there is mismatch at any point, that means the entire tree is different. The two trees are different. So the interesting thing is how to do the traversal. Okay. Yeah, so try this. It's very important. It will check your coding skills in both recursion as well as in binary trees. Yeah, so I have a final here third exercise for you to do. Okay, so I'm sure well, I'm not sure. maybe you have heard of this famous cartoon series called The Simpsons. So this is the Simpsons family tree. For my example here, I have only used a very small part of the tree, this part, okay, which I have marked out. Okay. But if you take a family tree, they tend to be very large. Okay. So I have a question to you. If you have such a big family tree, okay, a very large family tree, how would you store the details? Would you still use a tree? Because obviously this can't be a binary tree. Okay, because if you can once you get the PDF, you can zoom and see the tree structure more clearly. It's not a binary tree. It has in a given node more than one more than two child nodes. So how would you actually store this? You can carefully think about this based on the data structures we have discussed and come to a conclusion. Okay, so that finishes this series of lectures on using data structures for problem solving.